Hello, welcome to CS with Terry. Starting from this video, we will publish a series of videos to talk about sorting algorithms. We will call this series Essence of Sorting Algorithms. Sorting algorithms are relatively basic among all the algorithms. The goal of sorting is to arrange the elements in an array in a certain order. Even though sorting algorithms are basic, it captures the essence of algorithmic design. In this first video of the sorting series, we discuss three simple algorithms: selection, bubble, and insertion sort. Let's first take a look at selection sort. Suppose you have a friend who has never learned programming. How would they sort this array? They might do it like this. First, pick the largest element in the array and move it to the end. Then pick the largest remaining element and move it to the end. Keep doing this and the array will be sorted. This simple algorithm is selection sort. Let's take a look at the pseudocode. The function selection sort has two parameters, a and n. A is the array we try to sort, and n is the length of the array. In this function, we can iterate on I from n-1 down to 1. In each iteration, we set max index as the index of the largest element from a0 to ai. Then, we only need to swap ai and a max index. We continue this process and the sorting algorithm will complete. The operation to identify the index of the largest element from a0 to ai requires another for loop. The code is presented here. Now, let's analyze the time complexity of this algorithm. When I is equal to n-1, j will loop n-1 times. When I is equal to n-2, j will loop n-2 times, and so on. We can thus find the pattern of how the number of times j needs to loop through changes. Sum them up, and we can get n squared minus n over 2. So the time complexity of selection sort is O(n squared). By the way, we can also calculate the time complexity in a way similar to how we calculate areas. In this graph demonstrating the number of loops, each square represents an O(1) operation. The sum of the areas of all the squares is the time complexity of selection sort. Since the shape resembles a triangle, we can easily figure out that its area is approximately n squared over 2. This also tells us that the time complexity is O(n squared). Next, let's look at bubble sort. Bubble sort is similar to selection sort in that they both move the largest element to the rightmost position. How they are implemented is, however, different. With bubble sort, we iterate through the array. If the element being iterated over is larger than its next element, we swap them. Then, the largest element would gradually arrive at the rightmost position, just like a bubble rising to the surface. For reference, let's call this operation bubbling. Then, we repeat the same bubbling action for the rest of the array, and can move the second largest element to the rightmost position. Keep doing this, and the array will be sorted. Let's look at the pseudocode of bubble sort. The effect of the function bubbling is to bubble elements in the subarray a0 to ai. Specifically, we let j iterate from 0 to i-1. If aj is larger than aj plus 1, then swap aj with aj plus 1. Next, we look at the function bubble sort. We let I iterate decreasingly from n-1 to 1. In each iteration, we call the function bubbling. To simplify the code, we can combine the two functions into one. Now let's analyze the time complexity of bubble sort. Since the iterative process of bubble sort is almost the same as that of selection sort, its time complexity is also O(n squared). However, we can make minor modifications to the code to improve its best-case performance. In each iteration over j, we can keep a record of whether there are any swaps. If there is none, it means the array is already sorted and we can exit the loop. Here is an example. Suppose the array looks like this. The array is already sorted after the first iteration. During the second iteration, since there is no record of swaps, the function exits the loop. Here is a graph representing the number of iterations. Thus, its best-case time complexity is O(n). Of course, in general, since elements in arrays are random, the time complexity of bubble sort is still O(n squared). That's because the loops usually proceed to the last few layers. Finally, let's look at insertion sort. Insertion sort is pretty similar to drawing cards. At first, all cards are on the table. Then, I draw the cards one by one. Each time I draw a new card, I insert this card to the appropriate position so that cards in my hand are always sorted. Thus, all the cards are sorted when we finish drawing them. Here is the pseudocode of insertion sort. Let's first look at the function insert element. What it does is inserting AI to the correct position, given that the subarray A0 to AI-1 is already sorted. Here, A0 to AI-1 is analogous to the cards in our hand, and AI is analogous to the new card. Now, let's examine how this function is implemented. First, we let new card be equal to AI, which represents a new card. Then, we iterate over each card in my hand from right to left. If the card is larger than the new card, we move it one position to the right. Or let aj plus 1 be equal to aj. Finally, we find the position of the new card and let aj plus 1 be equal to new card. Then, let's take a look at the function insertion sort. In this function, we just need to let I iterate through 1 to n-1 and call the function insert element in each iteration. In other words, insert the new card AI to the correct position. This concludes the insertion sort algorithm. Again, to simplify the code, we combine the two functions into one. Next, we analyze the time complexity of insertion sort. It is a bit more complicated, so we will discuss a few scenarios. In the first case, suppose the array is already sorted. Then each time a new card is inserted, the iteration of j will quickly exit. In other words, the iteration of j has time complexity O(1). The total complexity of the algorithm is O(n). In the second case, suppose the array is inversely sorted. Then, every time a new card is inserted, it is the smallest one. In this case, we need to iterate to the leftmost position before we find the correct position for the new card. In other words, there will be one iteration when I is equal to 1, two iterations when I is equal to 2, and so on. Using the triangle area analogy, we can get the total time complexity is O(n squared). In the third case, suppose the array is completely random. Then, the correct position of the new card could be anywhere in the array with equal probability. So, the average position of the new card is in the center. Thus, the graph representing the expected number of loops should look like this. It is still a triangle, albeit a smaller one. Its area is about n squared over 4. Thus, the average time complexity of insertion sort is still O(n squared). We have introduced 3 sorting algorithms. Now let's compare them. The best, average, and worst case time complexities of selection sort are all O(n squared). The best case time complexity of bubble sort is O(n). That's because if the array is already sorted, the iterations can stop quickly, but its average and worst complexity is still O(n squared). Although the average time complexity of insertion sort is O(n squared), the same as selection and bubble sort. In actual applications, it is usually more efficient. That's because it usually needs smaller number of iterations than selection and bubble sort. We can see this clearly from the graphs representing the number of iterations. However, when the data size is large, none of the three sorting algorithms can sort arrays efficiently, since their execution time grows according to the square of data size. In following videos, we will introduce some more efficient algorithms so that they can sort arrays quickly even if the data size is large. Before we end this video, I'll leave you a question to think about. For a pair of numbers in an array, if the number in the front is larger than the one in the back, we call them an inversion. The total number of inversions in an array is its inversion number. For example, the inversion number of this array is 6. So, what is the relationship between the inversion number of an array and the time complexity of sorting it by insertion sort? That's all for today's video. If you like this video, please hit the like button and subscribe to our channel. If there are topics you are interested in, please leave a comment. Thanks.